a lot of topics, slowly building up the pace. Uh, Last class we covered support vector machines. There were two problems. One was what if noisy data comes into picture, and what if the decision boundary itself is not linear? What do we do? Because SVM by default will only do linear boundaries, right? So then what do we do? So one of the ideas was to push it to a high dimensional space, like all the inputs that we have, to push it to high dimensional space. And in like the assumption is in high dimensional space, probably we will get a line that cuts it. Yes, like very nicely, as in a hyperplane that cuts it, and so that we will have still a SVM will still be making a like a linear cut, like a linearly separable cut. But if you then move it back to the older dimension, that might look like a nonlinear cut. Yeah? So just to give a, very small recap. So I hope you remember this. So here you have the, if you look at the right hand side, there are blue dots and the red dots, the one that we had last time. And if we do this quadratic uh, kernel, so this will basically be exposed to a three-dimensional space. And then we can eventually have an hyperplane that separates the like nodes or like the data points in a different class from another class. Yes, that's the goal with the quadratic kernel. I hope this was like super clear in understanding. And if you look back and if you just plot it back, the like the decision boundary to a two-dimensional space, this will look like a circular boundary. Yeah, might not be super circular, but circular boundary. Yeah. Now the next one was the RBF kernel. Again, I told you like this is one of the most used kernels that are there. And if you look closely, so here on the top part, this is like x minus x prime. You can call it like xi minus xj also. Like there are two data points, and basically you're calculating norm of this. Yes, so you can assume those to be like distance between those 2 points. Yes, and then we are doing an exponential on top of, then we are dividing by let's say 2 sigma square. Hmm. And or otherwise, if you look at other literature somewhere, it's also like instead of 2 sigma square, here there will be like a gamma that is multiplied. Yeah? So it will be looking like a negative gamma of x minus x. Yes. But otherwise, this is equivalent, like gamma will be equivalent to 1 over 2 over sigma square. Yes, that's the only difference there. Nothing else. I just wanted to have a like a brief. I wanted to tell these pictures I borrowed from a YouTube nice link. I have posted the link at the end. So this is a nice diagram to illustrate. So let's say I have a bunch of points, yes, and the whatever you see in the right petri dish kind of style. So I have a bunch of points there, and what I want to do is basically apply RBF kernel. So if you look at this kernel very carefully, what it says, what will be the maximum value? It's e to the power minus x, let's say. Yeah, so the maximum is like, let's say it can be like that means the points are basically overlapping over each other, so e to the power then x minus x will be 0 in dimensional space, and then the entire thing becomes 1. Or otherwise it could be like they are very far away, let's say infinite distance, and then the entire thing becomes 0. So overall this kernel's value will vary from let's say 0 to 1. Fine. So I hope that is getting clear. So it is distance between 2 points. The value of this kernel, when we push it to high dimension, it becomes, let's say, the value will become 1 if it is overlapping, or closer to 1 if it is closer. And then if it is very far, like very far, it will become 0. Yes. And then like the sigma is like 1 over sigma. If like for example, if we had very high sigma, so even if they're overlapping like very close to each other, the sigma, if we have like 100 and 100 or 1000, then this will divide it by a large number, right? So then again it will fall down towards zeroth space. Hmm. That means if very high sigma values, I'll be only giving high values closer to 1 if they're very close to each other, right? And if very low sigma values if I have, then I'll be asking, like I'll like spread a very wide net, right? uh, Give me like one moment, sorry. हाँ, हो ठीक है. So sorry. Uh, Fine. So I hope this is clear. So this is distance between 2 points. Yeah. Uh, it's near to one if they are closer to each other, closer to zero, like near to one if it is closer, then closer to zero if it's far. And sigma will decide how close we want the points to be or how wide the points we want to be. Yeah. So if you look at then this petri dish, if you try to assume that the point in the red is the point at the concern, like point of concern, and from there we want to find out all the distances, right? Or we want to find the k function, yes, the kernel value. So this one eventually will look like this. Yeah. So that means that that point, everybody that has values closer to each other, that particular function gets higher value. That particular point gets higher value, so that increases, and anything that is very far away, that will be like closer to zero. Yes, so that looks like a Gaussian curve at that particular point. Yes, the width of the Gaussian curve and the like how steep or like the steep is Gaussian curve, that will depend on the sigma also. Yeah. uh, Now, like after we do this, what happens now? So the goal is then, if you look at this, like this is for one distance, and similarly we'll have across for everybody else. And slowly for every distance that you calculate, you will have some overlap of multiple this Gaussian stuff, right? And then the values that are closer to each other, they will like have high values, and the values which are like far away from themselves, they will have lower values. In two-dimensional to three-dimensional, probably we are able to visualize, but this is happening in multiple dimensions, right? Based on what x is, of course. And this is like infinite dimensional kernel. And then if we do a slicing across, again, that's an hyperplane slicing. Based on that, we will have separate stuff. Yeah. I will just show you like the code for it, like few of the diagrams, nothing basic. I think the major thing I have, like the note I will share anyway. Let's see, continue. Okay, okay. I hope this is visible. Yeah. So I just wanted to highlight few things quickly. So there is from sklearn itself, we can use sklearn and we can use SVM. And there is like similar like linear regression, decision trees like the cart and ID3, and similarly we can use SVM. And once we have SVM, the function looks like the use application of the function looks exactly the way we think it should be. That's it. Most of the times you will see it will be like dot fit, right? The model dot fit, right? The model could be linear regression, could be logistic regression, distant tree, or SVM. This dot fit, even we go to like other fancier neural networks and deep learning, they will also have a similar function called fit. Fit is just a nomenclature, but that's what we use. But this is the idea, yeah. And you remember the hinge loss. Hinge loss is if you looking at C, then this is like hinge loss values, yeah. So this is a diagram. I'll try to find out if there is some fancier. Yeah. So here, if you see, these are all like blue points. I hope this is visible in some sense. So the blue points are there, the red points are there. Using linear kernel, can we decide? So this will always be a line. Like linear kernel will be line. Polynomial kernel will have some polynomial attached to it, curve attached to the line itself. Then this is the RBF, where like where the closer the points are, the values are higher. Yeah. And then again, these values are higher, and somewhere in high dimension there is a cut that exists. That cut that exists, eventually that is an hyperplane in the high dimension, but that cut looks like this. Yeah. And similarly, these are all different data set. There's a circle data set. This was, I think, linear data. And this one is like a moon's data. And similarly, we have drawn the curve. Yes. So there is an RBF kernel. There is a sigmoid kernel as well. Yes. So on and so forth. And based on the cut that we have and based on the sigma values, you will have decision boundaries across. Okay. This is one. I'll show you that. and maybe this. So this is also I want to show here gamma is written. Gamma is basically you can assume like 1 over 2 sigma square. That is the gamma, same principle. So as you can see, if the gamma is like low or and instead of that becomes high. So if you see what eventually is happening, the decision boundary is going like closer and like it's going far away from this one. It's not very super general. Yeah, you will move either to the red points. Then that is not super general. There is some noise, but it tries to make no losses at all. Gamma is equal to 1 and C varies. So the decision boundary gets constricted to very smaller areas. Yes. And then similarly, if you look at like if the gamma is super high, it like there is a high number here 100. So the decision boundaries are like super close to each other, right? So there is the cut has been made so that the super high values only get to one other class and the other values get into other lower class. But you see the decision boundary is so close to the point, right? There is no generalization happening. Yes. And if you also look at support vectors, there are 59 support vectors here, 24, 100 and 109. So if you look at if the more and more support vectors you keep on asking, then your distant boundary basically becomes very, very small and tiny pieces and every point will matter, right? It doesn't become generalized. It becomes more memorized as you go. And this is like a super oracle style thing. Same like the height of the decision tree where height control the inductive bias, we called it an hyperparameter. Similarly, gamma here would be an hyperparameter for RBF kernel based support vector machine. Yes. So the moment you vary the gamma, sometimes it will become memorizable or oracle or basically it does not care about the data. And somewhere in the middle is generalized. Yes. And this basically shows like how far the Gaussian thing is, like as in if you can see this shows the spread of the entire Gaussian at that particular point if that is a kernel center. And based on the value of gamma the Gaussian like center is chosen, and that's how like basically the spread is identified. Because the spread in the last kernel where gamma is very high and let's say the spread is very small, so every point in this figure gets its own decision boundary around it only. Fine. So it's just very steep Gaussian curve. Yes. Rest all points are 0 to him. Right? So like all of you are dead to me because you are very far. I will only consider which are very close to me. That's the idea. Yeah? And that is there. And this is also another graph. You can all please try. And also if you find any mistakes in the notebooks, please let me know. We will correct it. And the similar case here, these are some other data sets and how RBF, if you vary things, how things are changing. Yes, excellent. So that's what I wanted to cover from this particular thing for at least SVM recap. Sharing back. Okay. So I hope you have had like some idea now on SVM, and with that, we have covered linear, logistic, decision, and SVM. And if you look at all of these are all functions that have some weight and some bias. Yes. And SVM, though, of course, they have a bias like W and B. Decision trees also have a W and B because like you can calculate the loss function also based on gene impurity and all those. It's not a strict learnable thing. But generally some parameters are chosen based on that. Parameters would be like what split to take, that is the parameter. Probably. And then next you have logistic and linear regression, which have their own parameters, right? So all these that we have studied till now, they are all like parametric. That means we are trying to optimize W and B based on the input data, some form of W and B, not exact maybe. And these are supervised. Yes. What is the inductive bias of SVM? So this depends on, like, for example, inductive bias would be like, I want to have the highest margin. That's the goal here, for example. And you can talk about, it's not a single inductive bias per se, like multiple hyperparameters control multiple hyper. but major is the decision boundary, right? So if I create a decision boundary that, for example, wherever the noise is, we decided some inductive bias there. So if I allow my decision boundary to be somewhere in the middle and accept noises, then it maximizes and becomes more generalized. Hmm. Uh, or otherwise, if you look at this kernel space, like if I move it high, then depending on the gamma, this one moves. But generally, it's the question is on decision boundary. How far is the decision boundary from the support vectors? Yes, and what are the support vectors? Okay, and biasness is if the points are closer to each other, they're probably belonging to the same class. That's the because RBF, if you see particularly, they look at the distance. That's the closeness it is looking at majorly. And any other, if I have this polynomial kernel or quadratic kernel, that is also like we are trying to find a hyperplane distance, but where the distance from the margin has been quadratized, right? So all the distance in the high dimensional space has increased. Yes. So majorly it's distance between each other that decides the margin, and that's how it works. Yes. Fine. The next thing that we are going to decide, I hope that is somewhat clear. We'll discuss, keep on discussing also, but I was planning to put. So now KNN, KNN, that's why I told parameters. KNN is the first algorithm that we are learning, is non-parametric learning. That means there are no weights and biases to be optimized here. So what is k-nearest neighbor? So again, non-parametric learning algorithm. It is a majorly an instance-based learning. It's like a, or you could say like a lazy learning. Uh, the only thing here is it will keep all the training examples in memory, and there are no explicit model building phase. That means you do not create a function f. Yeah, and you make predictions based on similarity to the training examples. Yes, and unlike other algorithms, for example, if you look at SVM and all others, once the decision boundary is created, we don't care about training data set. We'll just use the decision boundary to answer the question. The sign of f of x. Similarly, in linear regression, everything, we don't care about training data set. But in KNN, we need all the training data set. Always continuously because we are not finding an f. That's the goal between parametric and non-parametric. And so what is the KNN's inductive bias? So nearby points have similar labels. Uh, Closer to some RBF, but RBF still requires a decision boundary. It's a little bit more two-step going there, but this one is much more clearer. So here says negative biases, nearby points have similar labels. This algorithm is super simple. Most of you have already done it, I think, somewhere or other. So you will consider a test point. So I'll give you training data points on the space, whatever you have. And there I will give you a new point. I will ask you that is it positive or negative? What you're going to do is, uh, let's say positive or negative or any other class. It can do for multi-class as well, not an issue. So the core assumption is if my points are closer, then they probably have the same label. That's the goal. And the algorithm is store all the training example, take a point, find the most similar test examples. Here, if you ask only one similar neighboring node, then that becomes like a 1NN stuff, neighbor nearest. But we want to ask, let's say, KNN. So if we ask K nearest neighbors, their labels, and then we will either average out or take a majority vote. We will do averaging in when we want regression. Let's say I have a point here, I have other points around me. I'm asking k nearest points. Tell me what your value is. Everybody says like 10, 10, 10, and 5. Okay, so now the average is, let's say, 8.2. Yes. And so based on that 8.2, now it becomes my value. Or otherwise, if I have red, 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 and blue, I will take a majority vote out of those. This is assuming k is equal to 4. Yes. So now I will take a majority vote. So okay, now 3 people are saying red, 1 people is saying blue. So my label will be, because I'm whatever the closest points are, I'll take red. The algorithm is super simple. Yes. And the only problem is prone to noise. We will look at it through the figures in some time. One of the issue is like label noise overfitting. What we will come back. We'll try to formally define it in later classes. Uh, Here, what happens is now if let's say my k is 1 and I have because there is a mouse here and there is a phone here, I'm asking what is this? Let's say mouse is the unknown point, yes, and I have a phone here. So it will basically ask like what is the label of my, let's say this one, of this one. This one can say okay, this is also a phone because there is another phone nearby it. Yeah, but there are other things like let's say keyboard is there, trackpad is there. Yes, so it could have told computer accessory, but those are far away. If my k would have been equal to 3, I could have asked my phone, keyboard, and trackpad. Okay, majority of them are computer accessories, so this one also is a computer accessory. Yes, but that's not the case. So if k is very small, then it can be prone to noise. Yes. Uh, so that's why like single nearest neighbor can be an outlier. It's not that single nearest neighbor can be outlier also. There can be like two outliers also, right? So if I have let's say two water bottles nearby and then other computer accessories nearby, but they're a little bit far away, even with k is equal to 2, it can still tell that this is a water bottle. Yes. So that's the difference. So that will be making unnecessary errors due to noisy labels. So what is the solution? You instead of asking just one person, you ask more persons. Yes, of course you can consider k nearest neighbor. That's why the algorithm is knn, and let them vote for the correct class. Majority will win, or we can take an average where we get the regression values. Yes, so algorithm is super simple. There is no function to be learned. All we are running is we ask the entire set of k. Yes, all the points, or like the k nearest points, and then we have the entire training set, but take a point and then only ask the k nearest neighbors. Whatever they give the solution, whatever they tell us in majority or average, we take that up. Algorithm is super simple. Take everything, find k nearest neighbors, and do this. Yes. Now geometric intuition behind it of course is like uh, we can use all the because KNN relies on what is nearest, and nearest we find out through some metrics of distance. Uh, then all the geometric concepts come into picture. Yes. So we can have this like biggest advantages. Of course, we can once we start representing vectors in high-dimensional space, we can apply geometric concepts to the machine learning for findings, especially the KNN thing. Now, distance between two vectors, very simple. We can find Euclidean distance like AI minus BI square and then summation across all the dimensions and then taking root over. There's general Euclidean distance formula. This is the same formula we can use to do KNN also. Hmm. And not because it is just geometric distance, that means which is nearest. To answer the question, which is nearest, Euclidean distance is one of them. We can use cosine similarity as well. Then we can use Manhattan distance, Chebyshev distance, and Hamming distance. All of the distances that you can ever find, all of them are applicable here. Yes. Uh, and then, like, how do we choose K? The bias and variance we will talk a little later. So, but you can feel the difference, right? So, like, that means if K is equal to 1, if my noise is closer, it will make noise itself. Is k is too large? Yes, we will also see that. So now k is the hyperparameter that controls biases, inductive biases. My decision depends on who is the closest. Yes. Now, how do I find is don't pick small k, don't pick very large k, rather you pick something in the middle. That's the answer. And of course, if you want to find out majority of a vote, that means you need to have odd number of neighbors, right? You cannot have four nearest neighbor. Somebody says two are red, two are blue, you are stuck. What will you do? Yes, so rather have an odd. And cross validation, I will cover that in later. And inductive bias, I told you, locality it depends here. So nearby points have the same label. There is one more thing that we here we do, and just to point out, there is also like feature equality. Feature equality means all the features are important. So here, if we calculate the distance of let's say point of xi and yi from another x1 and y1 from another x2 and y2, if you have to calculate the distance, we do not basically how do I say? We assume that all the features are important. That means xi and x1 and x1, xi and yi both are important, right? Now the problem is, and they're equally important. So that means we do not like order any of them. Yes. One example I just wanted to put it, like for example, let's say we want to classify cricket players by position. Yes. Now what happens is for every cricket player we have age and let's say annual income. Yes. Uh, uh, Here, for example, age will vary, let's say 18 to 40. Okay, maybe there are younger players now. So let's say 18 to 40. The age will vary. Maximum age is 40. Okay, that is also now tricky. And now income varies from, let's say, like 50 lakhs to, like, say, 1500, like 150 crores. Okay, so there are cricket should get. And if we just find out the distance between 2 points, and every point is a human player, and every human player has two features called age and annual income. Yes, because we treat every feature as equal. If you see, age can be difference. For example, if you see without knowledge, 25-year-old earning 500 lakhs will appear closer to a 35-year-old earning 600 lakhs. Yes, rather than to a 25-year-old earning 100 lakhs. 25-year and 2400, they should be a little bit closer because they're closer in age. Maybe age should play a factor. But here we cannot tell because the difference between 100 lakhs and 500 lakhs and 500 to 600 lakhs, that basically, because the gap is too much and we consider all the features equally. In age, we see a minor difference of 1 year age gap or 10 years age gap. But if you see in the income, we see like 100 lakhs of difference. Yes. And if we do find the distance between these two, the income basically that dominates the distance that we can get from age. So there has to be some sort of normalization done across features, or maybe some weight has to be given across features. Yes. And majorly, and some of the things also, like what weight has to be given, that becomes hyperparameter again, we have to select. And when you do, like for example, you will, KNN is a very nice algorithm, you will apply for your stuff as well. And it's very hard to beat KNN also, like, by the way, it's a very nice algorithm. Yes. And if you do this, you have to also make sure that the features that you have selected in doing some form of classification, some form of regression, they are not, like for example, either they are normalized or you weight them, like assign some importance to each of them based on your domain knowledge. Okay, you have this many, like 5 or 6 features for a particular material, you think this feature is more important than the other features, that you can do. Or you can normalize, of course, but even normalization also plays a very tricky role. That also does not solve the entire problem, but your domain knowledge can help us. Yes. Fine. And decision trees, the contrast, you, I hope you remember. So here in decision tree, when we build the tree, we ask which feature is important. That feature gets pulled up, and that's the first question that we ask. That becomes the primary split. Yes. And based on the height, only few features are asked. And that few features that are asked, they are, we have selected based on our decision tree algorithm. Yes. But in KNN, all the features are important and we find distance across all of them. Yes. Excellent. So now advantages and disadvantages, of course, like KNN advantage is it's super simple. I hope all of you have an idea now how to implement KNN. Take a point, find the k nearest neighbors using some distance metric, and whatever is this, take a majority vote. If it is this one, voting can be done not by majority, you can have other voting techniques as well. And the other thing is, or if it is a regression task, you can take average, max, min, or whatever you want. If there are any other ways to do so, that also you can do. And it also takes no assumption about data distribution. Data can be distributed the way, linear separable, we don't care. Quadratic space, we don't care. Too much far, too much close, nothing is care. Data distribution KNN will take care based on whatever the value of k is. Yes. And of course it is non-linear by default, right? So distance varies with, because the decision boundary will be created based on distance between 2 points. We will see how the KNN distance boundaries come. And also it's like locally adaptive. As locally adaptive here means basically at some places the decision boundary can be very far because the points are far from each other, and some points when they are very dense, like we have red points closer to the blue points, it will still try to divide them. Yes. So that's why KNN is super in that way. Disadvantages, The major disadvantage is, of course, like if you have k and n, you have, let's say, 1 point, and you want to find the k nearest neighbor. Yes, it looks simple, but to find k nearest neighbors for a computer, because for visualization, if I show you and then I tell you this is the thing, I'll give you a point. I'll ask you to find kth nearest neighbor. You can visually notice and then point. Yes, but assume it's like a computer which cannot visually push it in like 100 dimension vector, or each point is 100 dimension vector. Now how do we find k nearest neighbor? We have to query all of the points. Yes, so if I have n points, for a single point to find its k nearest neighbor, I have to ask every other point. Yes, fine. So that becomes huge, right? And that is just for this particular test. Again, another comes, keep on coming. For every point, I have to do the same exercise again and again. So store, that means I have to store the entire training data. I cannot just give away key, okay, I'm looking at only k points, I should store k. I cannot do that. I have to ask all the points. So that's why it's expensive in that case, and computationally expensive also because we have to calculate distance, which still is easy, but at least I have to do a subtraction, square, then root over if it's Euclidean, and the other methods will have their own complexity. And also sensitive to irrelevant features, like for example, if I have too many high dimensions, how do you rate them? Which dimension is important, which is not important? And for example, if you have added a feature, for example, let's say the city of the player, and somehow the city should not have played any role, but the city is now in the feature, so it's an irrelevant feature, but our distance calculation will depend on the city. Yes, so irrelevant features can definitely destroy what knn has to do. And feature scaling, of course, as we discussed, we have to do proper feature scaling so that it works fine. Yeah, and knn will fail when so specifically, if you look at this, if every point is equidistant to each other, then it gets no information, right? So that means this basically algorithm becomes useless. When something depends on distance and distance does not vary across points, then it's an irrelevant algorithm, it becomes. Next is noise. If it is has too much noise, and we know like KNN will look at noise portions, we'll see it in the figures also and diagrams. And then very large data sets, if we have you have to calculate. I told you for finding k nearest neighbor, you have to ask every other point. Now, of course, when to use KNN, small to medium data sets, nonlinear relationship if you have, local patterns are important, and there is no parametric model, right? So we don't want any parameters, we want train, we want an answer that is immediate. Yes, KNN is the best way to go. The pre-processing steps, I told one is normalization, standardization you can do, feature selection, some features should not be there, you should remove them. We can do dimension reduction, I will come to that later. And this is done. Uh, yeah. So the last thing before I end this today's Canaan stuff, I told you that to find the distance, I have to find k nearest neighbor. I have to query entire n. To give up on that, there are few algorithms that algorithms and data structures that will help you to reduce that space. That means I don't have to ask n points. Rather, I can ask a few subset of points and then probably get my answer. So one of them very easy is like, for example, KD trees and ball trees, which basically instead of storing, you can assume instead of storing the entire n points like in an entire data structure like plain one after another, let's say point where we have to query one. Instead, KD tree will store them in like small compartments where the small compartments will store the points that are closer to each other. Yes. So this basically makes things easier, right? So instead of querying all the endpoints, I can either ask one compartment or two or three compartments and get the answer. Yes. So that is one. There are also approximate methods so that we don't have to query, and there are like bunch of research work that goes in how to do KNN super fast. Yes, it's a very simple algorithm, but that querying, finding the k nearest neighbor, that is what takes time. Fine, and this is the reference for those images for today. I'll just show you the code for k. And like KNN is a very nice algorithm. You will be most likely you will be using it. Sorry. Fine. Okay. Yeah. I hope that is visible, KNN. Yes. So KNN is here. Yes. Just to sorry. Yeah. Let's see. Yeah, my bad. Sorry, I just wanted to find this line. So if you look at this line again, sklearn has knen as well. So there are like if you look at sklearn, under that there is a module neighbors. Under that there are two modules like k nearest neighbor classifier as well k nearest regressor. Yes. So again that model is here, and again to like find the we don't exactly fit the model, we just find out. So it looks like a fit, but that basically gives you an answer. Yes, there is no training per se. Yeah. So here, let's say k nearest neighbor. I hope everybody can see this diagram. So here the original data set is like red and green and let's say blue. And here there is a new point here. What should be the definition that is asked? Yes. So eventually the three nearest neighbors are, let's say these orange points. Looks tricky. This one looks closer. Yes. But let's say these three orange points are closer to this particular point. Then the query is if k is equal to 3, it is blue. So this point becomes blue. If you try to find out the decision boundaries, if you see anything that is within this particular small blue region that is there, that means the closest points, according to if we take k is equal to 3, all of them will have either all of the three nearest neighbors as blue or two, like the majority of them will be blue. And similarly for the red and similarly for the green. So based on that, the decision boundaries are created. And here, if you can see immediately, this is not like it is not restricted to binary classification, right? It can do as many classes as you give it. Fine. And then yeah. So then the hyperparameter is basically this k. What you choose, higher the k, that means the locality does not matter. Global things matter. Smaller the k, the locality matters. Yes, that's the fine tuning parameter that sits. Yes. So here, if you see k is equal to 1, if you will see the boundaries are very strict, they will have very close to the point. So I'm just asking my immediate neighbor to see. And this one will, of course, if I ask k is equal to neighbor, you will never have a decision boundary where there is a wrong classification happening, right? So it will be, I'm just asking me and my neighbor. Yeah. So if you see there in entire all these points, there are two green points. It is in the green zone. Again, similarly, all these green points, all these are in green zone. Even if in the dense areas, if you see, there is no issue. But the problem with taking k is equal to 1, if you see, like these are most likely noisy points. There's at least one that are there. But still, because k is equal to 1, they are important. That particular point is important. Now they will have their own decision boundary around it. Yes. Then we can end up with errors. Yes. The next thing is basically k is equal to 3, much more, that's not much more, a lot more relaxed. And so here, if you see, there's again decision boundary is there. It's still not smooth because k is still small. But if you see, it starts to making some mistakes. Some mistakes are allowed. That means because majority matters, so at least one neighbor could be from others. Yes. So if you see, the boundary has increased, but this has gone in. But these noisy points that were there, the one individual points on the left hand side, if you see that had decision boundary around it, now these are gone. Yes, but the larger, little bit larger clusters, they will still have their own boundaries. Yes, so that is gone. And then if you increase again k is equal to 5, more and more things happen. And similarly, if you make k is equal to 15, like we are completely ignoring any small locality. If there is a different class, we are ignoring them completely. Yes. So what is the best K? I will come to that. And if you see, so if we, there is no training accuracy per se, but okay, so assume I'll ask a question maybe later. But if you value the vary K, this is how we perform. Like this is how accurate we are. So if you see the red curve on the left hand side, just ignore the training accuracy for now a little bit. Just concentrate on the red curve that is there. So if you increase the value of K, like this is how accurate we are. That means this is how many, if you give me new test points, we are correctly predicting their labels at this accuracy. So on the left hand side, it's like 90%. That means we are predicting 90 out of 100 correct. Yes, zero point 0.9 if it is there. So this is the accuracy. And if you see like for k is equal to 3 or k is equal to 2, it is performing really nice. We can do this exercise and find out. Yes, but we should never look at test, right, to find out this, what is the good value of k. We should only look at training and find out what is the good value of k. Yeah. And for, but the problem is in training accuracy, k is equal to 1 will always give you full accuracy, because I will consider only myself. I will be always correct. Yes. So then how do you choose what is the best k? Hmm. That is there. I will come back to that question. And then there are other things I told you, like there can be distance is one of the areas of hyperparameter. Let's say this is also hyperparameter. We can choose Euclidean, Manhattan, and then Chebyshev and cosine. And if you see, k is equal to 3 in all these examples, but which points are neighbors, that varies based on the distance metric that you choose. Yes. So here these 3 points are there in Euclidean. On the right hand side, there is a one difference, and then Chebyshev has something else, and cosine has something else here. Cosine will move, like try to find out in the same linear fashion it is there from origin. Yeah? And this one is a query and data points. I'll try to see if there is something else. Okay, yeah. And the remaining example that is there. So the previous example that we saw is KNN for classification. We wanted to classify. This is KNN for regression. Yes. Here, if you see, like that means this particular line, the red line that is there, that is the actual true function that is there. Dot blue points are the training points. That means the red line was actual function, but that, so anyways, we are not going to get it in this thing. The training data points that might include some kind of noise. Yes. So those points are the blue points. And if we put k is equal to 1, it will exactly line up with that point, right? So it will follow the distance between 2 points. That means that I'll be far from here, close from here, far from here, close from here. Yes. So in this way, it will try to create the Kenan, and then given a particular x is asked, you just point the line in between. And as you increase Kenan, it tries to relax, that it should not be like, maybe like not all points are important, right? Rather, it will ask for an average of across all the points around me. Yes. So that's how this becomes a little bit closer. And then again, it becomes a little bit closer to the original space. But if you do it like k is equal to 20, if you keep on increasing k, it might go far away from the actual point. Yes, from the actual curve. Now this one looks the closest, maybe like one of them, probably k is equal to 3 and k is equal to 10. So those are like good values to pick from for regression. This is like a weighted KNN and unweighted KNN. Unweighted KNN would be like if those points are just, we take one, like the value can be just one, but somewhere if we assign their value to be their particular feature value, then that can be like distance weighted. Yes. These are all like metrics that you can try. I hope you will take a look at this. And this is a iris dataset. I think I showed you some time ago. Like this is the original dataset, and if we can do apply KNN on top of it, it will also works fine, and KNN is used very nice. And if you apply KNN on top of it, if you can see the red line, the blue line, and the green line for k is equal to 9, this is the distant boundary. There are few mistakes that are happening. There is nothing, no mistakes happening for red, few mistakes happening for, let's say, green, and blue, this is in the training set. When test comes, if something is closer to this lower blues, the ones that are blues on the green side, it might make an error, but majorly no. So that's the KNN. But then how do we choose the value of K, right? That's the question that is remaining. Any answers from audience? Any hints if you have? How do we choose the value of K? Any? We cannot look at test. That's definitely there. We definitely cannot look at test data. So then how do we choose K? If we choose K is equal to 1, of course, we'll get correct. Uh, Accuracy score in what? Like, for example, if we look at test already, that means we have already chosen K, right? So the moment we pick accuracy for test, then we are struggling. And if K is equal to 1 for the training set, then of course we will win. So then how do we find the value of K? Anybody else wants to opine? So this is the step where something called a validation set comes into picture. So moment I tell you that you have to find a good value for hyperparameter. Somebody else pinged again. No. So anytime I ask you like what is the good value of a hyperparameter? So here the K is a hyperparameter for KNN. You can use something called a validation set. What you can do here is basically if you take a training set, you're not looking at testing. Testing is far, we definitely not never looking at test. If you just take the testing, what you can do is you can keep some part of the training on the side. Okay. Then you can try to find out, you can fix, you can find K value. You can basically here, though there is no training involved. Some part of the training you can take as a validation, which is not test. It is part of training, but you are and you know the label of this particular few validation sets. You can ask the question which K is good on those validation sets. Yes, and we will discuss this in more detail, and that's why I think more and more time I think you would have heard here. Sorry, where did it go? This term I think came up like the cross validation. So that's the idea. So you can take small part of the training set output, and there you ask. Here we know this is not test data set. Here we know the labels, so we can ask questions based on the training set because our nearest neighbors will come from the training set. For this validation set, what K is good? The assumption is maybe this particular K, maybe this particular validation set is closer to the training as well as closer to the testing set. We could be wrong, but that's one way to do so. Yes. I hope that makes sense. We'll discuss cross validation in more detail. That is a little bit more more complicated technique than probably just taking one part of validation out. Otherwise, yes, that's it. Fine. So with this, we are done with 5 algorithms: linear regression, logistic regression, decision tree, SVM, and then KNN. Yes. KNN is non-parametric. Others are all parametric. You need to train the model. Yes, there has to be like a fit function that trains actually. KNN has like a fit, but that does not count any fit. It just finds the value immediately. And that's all. So we have covered all the 5 basic supervised algorithms. Next, we will jump to unsupervised algorithms next week. Uh, but before that, I think there is an announcement I would like to make for the course itself. Now, the deadline for those who are doing credit related, the deadline for you to submit the first, like the problem statement, was earlier this Friday, based on request from few of the people, and this has I have and discussed with Professor Sen as well. We are shifting the deadline to September 15th. Yes, that's a Monday. The website has been updated with the new due dates. So you guys all have more time to find the problem statement in material sciences using machine learning, if you can do anything. Yes. So the logistical update is basically we are changing the deadline due. And some other deadlines also have shifted by 10 or 15 days, so you can check that also. But fine, this one gives you more opportunity to work on the problem statement. Okay. And next week we'll cover this one. And Friday there is no class. We will meet on Monday next week, September 8th, I hope. Yeah. Okay. If there are any questions, please go ahead. Otherwise, today's class is done. So the simple class on KNN. Okay, we will end the class here. So what I'm saying is, if in case there are any questions, drop us an email. And otherwise, the deadline has shifted. We have covered all the five basics, notebooks, and everything is up. Please try to practice so that will give you more ideas on what to do and what not to do. Yes. There are some concepts here, of course, like overfitting, bias, and variance. We will cover them. They're supposed to be part of this slide. That's why I put them. But we'll cover them in more probably next week or the next week. Okay, fine. We will meet on Monday. Fine. Bye.